All right. Hello, everyone. Happy Thursday. It's Mr. D here again with another remote learning lesson for you guys. Today we'll be doing 5.5 and 5.6. The sections are on symmetry and functions. Our learning targets for today are I can identify even and odd functions by their graphs. I can complete even and odd functions if I know what half of the graph looks like. And I can identify even and odd functions by their equations. So for task one, they give us these two kinds of graphs. They're divided into set A and B for us here. The first question it has for us are how are all the graphs in set A similar and how are all the graphs in set B similar? So go ahead and pause the video here, take a look at the graphs in column A, the graphs in column B, see if you can come up with any kind of similarities between the two of them. Okay, so here's what I wrote for my response. I said in set A, all the graphs are symmetrical about the y-axis. What I mean by that is if we look at any of the set A graphs, if we look at, say, just the right half, and then we reflected that right half across the y-axis, we would end up with the left half. The same goes for if we looked at just the left half, we could reflect that across the right half, or across the y-axis, and we would get the right half. Then I said in set B, all the graphs are symmetrical about the origin. So if we take a look at, let's use this middle one as an example. If we were to take each point on the right-hand side of this graph and draw a line directly through the origin and went the same distance through to the other side of the origin, there would be a point on the left half of the graph. We can also think of this as being a reflection across both the y and the x-axis. Let me see if I can do a little drawing here for you guys to show you what I mean. So let's say we had a graph that looked something like this. Let me draw the other part of the graph as well. So if we were to reflect this first across just the y-axis, we would end up with something that looks like that. And then we reflect it also across the x-axis, we would end up with something that goes straight through the origin in the same direction but opposite as the left part of the graph. So with that being said, we have a couple definitions. So the graphs in set A are all even functions. According to our definition here, an even function is a function f that satisfies the condition f of x equals f of negative x for all inputs x. You can tell an even function from its graph. Its graph is symmetric about the y-axis. So what this definition is telling us is that if you take any input on an even function and change the sign on that input, the output of the function will be the same. Let's go ahead and look at an example up here. We can see on the first graph in set A, we'll use 2 as our example here. F of 2 is right here at this point 3. F of negative 2 has the exact same output as f of 2, also 3. If we look at f of negative 4, that's going to be this point on the graph right here, its output is 0. Switch the sign on that, f of positive 4's output is also 0. So for even graphs, changing the sign on the input will give you the exact same output. Our next definition is for odd functions. An odd function is a function f that satisfies f of x equals negative f of negative x for all inputs x. You can tell an odd function from its graph. The graph is taken to itself when you reflect it across both the x and y axes. This can also be seen as a 180-degree rotation about the origin. So let's go ahead and take a look at some of our odd graphs here. I'll use purple for drawing. Hopefully that'll be a little bit easier to see. So if we were to take, say, any input, we'll go ahead and look at f of 2 on this graph. we can see that its output is right here at 1. If we were to reflect this across both the x and the y-axes, we'll start by reflecting across the x-axis. So we would go down instead of up, and we would end up at -1. Then we would also reflect across the y-axis, and that would take us over here to -1 on the y-axis. So our input for f of 2 is +2, and our output is 1. When we plug in -2, we get -1. So this is a reflection across both the x and y-axis, or you can think of it as, say, a 180-degree rotation. If we were to just take this and rotate 180 degrees, we would end up at the same point. So let's go ahead and look at the next question for us. Now it wants us to identify whether the following graphs represent even or odd functions. Explain your reasoning. So pause the video here, take a guess as to whether these are going to be even or odd, function f and function g, and give a brief description of why you believe that. So here are the responses I came up with. Feel free to have slightly different explanations here as long as they say something similar. I said that function f is even because its graph is symmetric about the y-axis. If we were to look at, say, just the right-hand side and imagine folding this across the y-axis here to the left-hand side, the image of what we got from folding it would be the exact same as the way the graph currently looks. For function g, I said that g is odd because the left half of the graph is the same as the right half rotated 180 degrees about the origin. So again, if we were to imagine rotating this in a semicircle around the origin, we would end up with the exact same graph on the left-hand side. And again, this can also be thought of as a reflection across both the y and the x-axes. If we were to take this and reflect first across the y-axis, we'd have something that looks like that. And then when we reflect it down across the x-axis, it would land right on top of the graph that we currently have. Okay, but there was another part to our definition too. It wasn't just talking about the graphs. It says an even function is a function that satisfies this condition. F of x is equal to f of -x. It says that an odd function is a function that satisfies f of x equals negative f of -x. So again, what this is saying is if we change our input to negative, the outputs will be the same. F of x and f of -x have the same value. So if we know what f of 2 is, and we know that the function is even, we also know what f of -2 is. Plugging in -2 would give us the same thing as plugging in 2. For odd functions, when you change the sign on the input, you also have to change the sign on the output. F of x is equal to negative f of -x. So if, say, we know a function is odd, and let's just imagine that f of 3 was equal to 9, then that means f of -3 would be equal to -9, because for odd functions, changing the sign on the input also changes the sign on the output. So using that knowledge, let's go ahead and take a look at this next task. It says, here is an example of a table of input and output values for an even function f of x and for an odd function g of x. So the first step is, for the even function f of x, what do you notice about f of 8 and f of -8? Is this pattern true for all values of x? Go ahead and write down something that you notice, and I will share with you what I came up with in just a moment. So here's the response I came up with. I said f of 8 and f of -8 are both equal to -1.5. This will be true for all values of x, since f of x is equal to f of -x for all even functions. So we can verify that this pattern is true as well. Don't just take my word for it. If we look at inputting -6, we can see that we get -3. Also, if we input +6, we get -3. If we input -2, we get +1.5. And if we input +2, we still get +1.5. So just verifying our definition on an even function, changing the sign on the input does not give a different result. The result will always be the same, whether this sign of the input is positive or negative. So next, let's take a look at number 2. For the odd function g of x, what do you notice about g of 4 and g of -4? Is this pattern true for all values of x? Go ahead and pause the video, get something written down, and I will share my response with you momentarily. So for number 2, my response was g of 4 is equal to negative g of negative 4. That is the same value but with opposite signs. If we take a look at our table here, we can see that g of 4 is equal to negative 5.25, whereas g of negative 4 is equal to positive 5.25. And then I said this is true for all values of x, since g of x equals negative g of negative x for all odd functions. Remember, what this is saying is just when you change the sign on the input, you also have to change the sign on the output if your function is odd. We can verify, too, that this is true for all values. If we look at 5 and negative 5 here, we get 0 for both of them. The only reason that we don't see the difference in signs here is because positive and negative 0 are the same number. But it's clearer if we look at negative 4 or 4, which we did for number 2, or negative 1 and positive 1. When we input negative 1, we get out negative 4. When we input positive 1, we get out positive 4. So changing the sign on the input also changed the sign on the output. So next up, we'll take a look at number 3. They give us these two tables, and they want us to explain how we can tell whether the following tables represent an even or an odd function. So go ahead and think about whether you think table A represents an even or odd function. Give your guess and your reason why. Do the same for table B, and then I will share my reasoning with you in just a moment. So hopefully you were able to get something written down for these. Again, if your explanation isn't exactly the same as mine, that's fine. My explanation was that for part A, this is an even function, since switching the sign of the input still outputs the same value. Don't be fooled by the fact that they're all 3's here. This still satisfies the definition of an even equation. We can see that f of negative 7 is equal to positive 3. If we switch the sign on the input and look at positive 7, we still get positive 3. F of negative 4 is equal to positive 3. If we switch the sign on that input and look at positive 4, we get the same value, positive 3. So we know that A is even. Go ahead and take another minute to pause the video if you still need to find an answer for part B, and then we'll talk about it. So for part B, I said that this is an odd function, since switching the sign on the input gives us an output with the same magnitude. And all I mean by that word magnitude is how big the number is, disregarding whether it's positive or negative, but opposite signs. So if we look at when our input is negative 3, we get negative 3.37. When we switch the sign on the input, we get the same number, but with the opposite sign, so positive 3.37. If we look at an input of negative 2, our output is negative 1. Switching the sign on that input would give us positive 2 for our new input, and the new output would be positive 1, the same value, but with a different sign. So we know that in this case, function B is odd. So next, we're going to be continuing with looking at these tables, but here we have some incomplete tables. It wants us to first guess as to whether the function will be even or odd, not necessarily guess, find out according to the definition. And then once we know whether each function is even or odd, complete the tables. So for part A, I would look at, say, negative 2 as my input. I see that I get positive 3, positive 2. My output is still positive 3, so I know that this one would be even. Because it's even, we know that the output is the same when the inputs are the same number but opposite signs. So I know, say, that for this box, because positive 4 gives me an output of 0, negative 4 would also give me an output of 0. So I'll go ahead and type that in for my response on here. We also know that because negative 6 and positive 6 are just opposite signs, that their outputs would be the same. So for these two boxes, rather, our outputs could be anything, but they just have to be the same value, since changing the sign on the input should give us the same result. So we could take a guess, say maybe it's going to be 5, and if the output, or the input rather, of -6 gives us 5, then the input of +6 also has to give us 5. So these two boxes could really be any number, but they would have to have the same value for each one. So using that one as an example, go ahead and pause the video, see if you can fill out parts B, C, and D on your own, and then we'll talk about what my results were as soon as you're done with that. A hint for you guys if you're having trouble getting started on this section is fill in the left-hand column first, the inputs column. We know that they're always going to be the same pattern. So say for part B, the first one in the left-hand column that we have to fill in would be -2, since we see a +2 as one of the possible inputs. And then since we already saw -5 as one input, we know that +5 would also be the other input there. Once you have the left-hand column filled in, filling in the right-hand one might be a little bit easier. All right, so let's take a minute to look at part B here. I know that part B is going to be a representation of an odd function because changing the sign on the input also changes the sign on the output. If we look at our input of -7, our output was +1. When our input is +7, our output is -1. Therefore, each of these pairs of inputs, where one is positive and one is negative, the output should be the same magnitude, but opposite signs. So when our input was +5, our output was +1. That means when our input is -5, our output should be -1. Next, we'll take a look at part C together. I think that C is going to represent an even function because we can look at the, oh, sorry, I lied. C is actually an odd function. If we look at when we input -1.5 pi, our output is 3. When we input +1.5 pi, our output is -3. So swapping the sign on the input does swap the sign on the output. Therefore, our function is odd. With that in mind, we know that an input of +0.5 pi gives us +3 as our output. So -0.5 pi should give us -3 as our output. So here we have two outputs that are the same but different signs. Don't let the fact that you don't see the negative on one of these fool you. Remember, 0 is neither positive nor negative. So these outputs could be anything as long as they are opposite signs of each other. So I'm going to choose -2 pi and +2 pi. Your values could be anything. It would still be true for the function to be odd. You could choose 500 pi. You could choose 1,000,000. Anything would work. So I'll just do -2 pi to keep it simple. I don't know how to type pi, so don't mind the fact that I just typed out the word there. I mean the symbol. I'm sure you know that. Looking at part D, I can see that Mr. Cardenas and I actually made a mistake when we were making this. We should have given you this one other input, -1 here. So sorry if you guys went ahead and were getting confused by that. You should have had that piece of information. So I can see that changing the sign on the inputs does not actually change the output's result. So when we plug in +1, we get -1.25. When we plug in -1, we still get -1.25. So that means that our function is even. If we look at the input of 2, we know that the output that we get for that should be the same as the output for -2. So when we plug in 2, we get -4. When we plug in -2, we should also get -4, since this is an even function. When we plug in -4, we get 0. So when we plug in +4, we should also get 0. So just a quick review of everything we've covered so far. We have these two different kinds of functions, even and odd. For even functions, their graphs are symmetric about the y-axis, and changing the sign on the input does not affect the output. The input will be equal to, or sorry, the outputs will be equal if you change the sign on the input. For odd functions, they are symmetric about the origin instead of the y-axis. You can think of that as either a reflection across both axes or as a 180 degrees rotation around the origin. And for odd functions, when you change the sign on the input, you also change the sign on the output. So with that in mind, we'll move on to task 3. For task 3, it gives us a couple of incomplete graphs. Well, actually, it's the same graph, but they want us to complete it in different ways. For part A, they want us to draw the other half of the graph if we assume that f is an even function. For part B, they want us to complete the graph if we assume that f is an odd function. So we know some things about the graphs of even and odd functions. Using that information, go ahead and take a minute to complete the graph on your own. I'll show you what my completed graphs look like as soon as a little bit of time has passed here. All right, so let's go ahead and talk about part A. We know that f is even in part A. That was our information given to us. So we know that this graph is going to be symmetric about the y-axis. Here we see this point, negative 1.4, 0.4. Because this graph is symmetric across the y-axis, we know that positive 1.4 will also have a value or an output value of 0.4. So let me go ahead and draw that on the curve right about here. We can also see that negative 3.4, negative 3.0 is on the graph. That means that switching the sign on the input will give us the same output. So positive 3.4, positive 3.0, or sorry, negative 3.0 will also be on the graph. So switch the sign on the input, keep the output the same. Using that information, I'm going to go ahead and try and draw what the graph will look like. So it'll be symmetric. On our left-hand side, we go down until we hit our negative 3.0 point, and then we have to switch directions and go back up. So I'm just going to try and do the same thing on the right-hand side. For part B, we're operating under the assumption that f is odd. So that means when I switch the sign on the inputs, I also have to switch the sign on the outputs. So negative 1.4, 0.4 is still on the graph. Now when I switch these signs, we also have to switch the sign on the output. So positive 1.4, negative 0.4 will be on the graph. That'll be right about here somewhere. Also, negative 3.4, negative 3.0 is on the graph. So positive 3.4, positive 3.0 will be on the graph. That'll be somewhere right about here. We also know that this other half of the graph will look like this same part if we were to rotate it 180 degrees, like so. Sorry, that is the worst arrow I've ever seen. Let me see if I can make that look a little bit better. There we go. That's a little bit better. So we just take this side of the graph and rotate it 180 degrees about the origin. We'll get the image of our new graph. So let's see if I can go ahead and try and draw that. So this is the graph that I was able to draw. It's not perfect. I'm trying to draw on a laptop here. Technically, this should be going through this point, but hopefully this is enough to give you guys an idea of what this section should look like. It looks like this section, if we were to reflect across both the y and the x-axes, or if we were to take this and rotate it 180 degrees about the origin. So our next task, now we're going to be thinking about our even and odd functions in terms of equations. So they want us to decide if the function is even, odd, or neither, and to explain and show our reasoning. So remember the definition of an even function. Let me go ahead and type these out for you here so that they're easy to see. For even functions, f of x is equal to f of negative x. So that means when we swap all of the x's with negative x's, we should get the same result in the end. For an odd function, f of x is equal to negative f of negative x. So what that means is swapping the sign on the inputs, in other words, replacing all of the x's with negative x's, should give us the same thing, but with a different sign. So let's go ahead and take a look at number 1 and see what we might be able to do with that. So first, I'm just going to find out what f of negative x is actually equal to. We know that it should be equal to f of negative x if it's equal, or if it's even, or it should be equal to negative f of negative x if it's odd. So to get an idea of what that looks like, I'm just going to replace all of my x's with negative x's so that we can look at what f of negative x actually is. So in this case, f of negative x will be equal to 3 times, and instead of x, I'm going to write a negative x to the 4th power. Unfortunately, I don't have a way to type subscripts and superscripts, so when you see this little caret, that just means in the exponent. So that 4 there is really in the exponent. Minus 2 times negative x squared. Plus 1. You know, I don't like doing it this way. I'm worried that these subscripts and superscripts are going to be confusing, so let me write that out by hand. I will be right back with it written out. There we go. Hopefully that looks a little bit better to you guys. So next I'm going to try and simplify this side a little bit. We know that negative x to the 4th power is really the same thing as negative 1 to the 4th power times x to the 4th power. But negative 1 to the 4th power, I'm just going to do scratch work over here. Negative 1 to the 4th power is just equal to negative 1 times itself several times and still gives us 1. That's supposed to be a 1, not just a straight line. So negative x to the 4th power is just going to equal x to the 4th power. Same thing when we look at negative x squared. We know that negative x times negative x, we've got 2 negative ones in there. When we multiply those together, we end up with a positive again. So this will just be equal to 2x squared. And then the 1 we don't even have to do any simplification on. That part is just going to carry through. So f of negative x then is equal to 3x to the 4th minus 2x squared plus 1. And if we take a look at what we started with here, they're the same thing. So because f of negative x is equal to f of x, we can then say that this function is even based on the definition of even functions that we have over here. So I'm going to repeat the same process on all of these and see if I end up getting something that is equal to what we started with or something where all the signs are swapped. So you guys go ahead and see if you can figure out whether any of these are even or odd. Go ahead and pause the video while you're working on that. And I'll come back to show you my work as soon as you are ready for me. Okay, so we'll start with number 2 here. I'm going to start this one off the same way I started off the first one by just finding out what g of negative x is. So I know that g of negative x will be equal to negative x to the 3rd power minus negative x. So all I did there was just replaced all of my x's with negative x's. Now, unlike in the first one, here we have odd powers attached to our x. So if we know that negative x to the third power is really just negative x times negative x times negative x. If we have three negatives being multiplied together, our sign is going to remain negative in the end. Two of them would cancel out, and then the third one would bring us back to negative, right? So this is going to be equal to negative x cubed. Here we are subtracting a negative x for our next section of the equation, and we know that subtracting a negative number is the same as adding it, so plus x. Notice that this result that we got here is the same as what we started with, but both of the signs are swapped. We could also rewrite this if we wanted by factoring out a negative as negative x to the third power minus x. That third power looks pretty bad. Let me see if I can make that look a little bit better for you guys. Maybe a little bit better. So does this fit the definition of our even or odd functions? Well, if we check our definition over here, f of x is equal to negative f of negative x. That tells us that our function is odd. So we know what our result would be here. I also realized that I never actually said on number 1 that it was even, so let me do that real quick. For number 1, we got even. Number 2, we got odd. Go ahead and pause again if you haven't done 3 or 4 yet. I'll come back with an explanation for those two next. So we'll go ahead and look at number 3 together next. I'll start this one off the exact same way I started the other ones off by finding out what h of negative x is equal to. So I'm just going to replace all of the x's with negative x's. So we'll have negative x squared minus 1 times, oh, just realized I made a slight mistake here. Let me get rid of this extra parenthesis. We don't want that one in there. There we go. That should be a 1. Times negative x squared minus 4. Okay, but we also know that negative x squared and positive x squared are going to give us the same thing, because when we multiply negative x by itself, the negatives will multiply to form a positive 1. So this will just equal positive x squared minus 1 times positive x squared minus 4. And since this has the exact same value as h of positive x, we know that this function will be even. Moving on to number 4 together. Started off the same exact way by finding out what j of negative x is. So we'll have 2 to the negative x power plus 2 to the negative x power we can drop some of the parentheses here. So 2 to the negative x plus, and negative x is just going to be positive x, right? So this doesn't quite look exactly like we had it in the beginning, but we know that because these are just being added together here and the order of addition doesn't matter, we can rearrange these. We can put the 2 to the positive x first and the 2 to the negative x second. So when we do that, it would look like this: 2 to the x plus 2 to the negative x. And now it actually does look exactly like j to the positive x does, right? So since j to the negative x and j to the positive x are the same thing, we know that this is going to be an even function. We'll take a look at number 5 together next. So first, let's find out what k to the negative x is equal to. So we'll have negative x to the third power minus 1 times negative x. Just replacing all of my positive x's with negative x's. So negative x times itself 3 times is still going to be a negative number. The 3 x's being multiplied means that we keep the cubed on it. So this will look like negative x to the third power minus 1 times negative x. So this doesn't look the same as it does up here, but it's also not just the same equation with an extra negative in front of it, right? Even if we were to factor out a negative from this first term here, let's go ahead and do that to see what that would look like. We would have negative parentheses x cubed plus 1. If we were to multiply that negative back in, that would give us back what we started with there, right? Let me make that look a little more like a 3. Times negative x. Okay, we could go ahead and also multiply this outer negative with the negative on the second x, right? Then it would end up looking like x cubed plus 1 times just x when we multiply those two negatives together. They're still not the same, right? This time we have, or in our original function, k of x, we have a minus 1. In k of negative x, we have a plus 1. So it's not the same equation. It's not just the equation with a negative attached to it. So that means for this one, it is neither even nor odd. That can happen sometimes. In fact, most functions are not even or odd. Even and odd functions are a special scenario that occur every now and then. But it's possible that you try finding out what k of negative x is equal to, or f of negative x, whatever your function is named as, and you don't get the same thing, and you don't get the same function but with a negative attached to it. And when that happens, it means that your function is not even or odd. All right, so our last one here is q of x. I'm going to start by just rewriting this in a slightly different form here. We could also think of this as x to the negative 1 plus x. We know that a negative exponent just means to take the reciprocal of our function. So if we wanted to, we could also think of it this way. It's up to you which form you use for this problem. They're both equally valid. So we'll start by finding out what q of negative x is equal to. So we would have 1 over negative x plus negative x. We can get rid of some of these parentheses here. This negative here, I'll use a different color here, we're allowed to pull up into the numerator if we wanted to, right? It doesn't matter whether the negative on a fraction is in the numerator or the denominator. So I'm going to write this as negative 1 over x, just pulling the negative to the outside, and then plus negative x. And adding a negative number is really the same thing as subtracting it. So this is negative 1 over x minus x. Okay, so we want to see if we can make it look more like our q of x function here so we can see whether it's even or odd. So in order to do that, I'm going to factor a negative out of both of these terms here. I'll write it as negative parentheses 1 over x plus x. And now we can see that it's the same numbers inside the parentheses here, except it has this negative value attached to it. So going back to our definitions, a function is odd when changing the input makes the output negative. So we know that our last equation here would be odd. And that is it for today's lesson, guys. Again, if you have any questions, feel free to attend Mr. Cardenas's tutoring sessions or office hours. Also, if it's easier for you, you can feel free to reach me by email. I'll go ahead and type that in here. It's my name at Gmail. Feel free to get a hold of me that way. I check it pretty often, so I should be able to get back to you quickly. Feel free to shoot me any questions. Hopefully this stuff is making sense to you guys. If it's not, I highly encourage you to go to office hours or tutoring. And I guess I will talk to you guys again next Thursday. I hope that your week has been good. Enjoy the rest of your day and stay safe, everyone.